Ladies and gentlemen, when it is 3 p.m. Central European Time in the beautiful city of Noordwijk in the Netherlands, here at the EPIC Control Station, welcome to Photonic Integrated Sensing. Welcome to EPIC.
Jose, I think there is no sound here.
You cannot hear the video, right?
No,
you cannot hear anything. That's good. You know, we try and we test electronics, and that's how electronics is failing us, and that's why we work in photonics, which is a much better and mature technology. Allow me to retry. Allow me to make you show the promo of this fantastic event. Monday, 20th and it works now, right? Season 2, Episode 5 of the EPIC Online Technology Meetings, celebrating the success of the industrial take-up of photonic integrated circuits for non-telecom applications. A lot of examples come to mind. Photonic integrated circuits is now used in LiDAR in harsh environments, including satellites. We are also using them in biosensing for the accurate and fast measurement of COVID-19. In fiber sensing, we have demonstrated haptic feedback to assist surgeons, or in gas sensing, where we can now cover the full mid-infrared band, accurately measuring NOx, CO2, and even TNT. Integrated photonics is very mature. To overcome the last stages towards industrialization, we need input from the end users about size, weight, interfaces, cost effectiveness, reliability, and lifetime. So let's do that. Join this forum of end users and big technology manufacturers on Monday, 28th of September at precisely 3 p.m. Central European Time, because photonic integration is essential for the next generation of sensing systems. Photonic integration is essential for the next generation of sensing systems, and for that we have the entire supply chain here, from design houses all the way to companies in the end user side. You're going to hear, for example, from Electrolux about the consumer market vision for integrated photonics. But the purpose of this meeting is always to connect. The purpose of this meeting is to find potential partners, suppliers, and customers. Today, I'm really happy to say that we keep growing. Today, we have already 620-ish members. The amount of members keep increasing. Thank you very much, all the photonic industry in Europe and worldwide, for keep supporting EPIC, for keep supporting what we stand for, the sustainability of photonics in Europe. And thank you for all the fantastic feedback that you keep giving to the team. We are so happy to keep doing this. I know these are not the best times for travel, so we brought the EPIC meetings to the comfort of your office chair. So last week, many of you attended, or virtually, the micro LED meeting. That was fantastic. Today, photonic integrated circuit for sensing. Next week, photonics for dermatology. We have a hot topic every week, and we work really hard with a fantastic team of 14 people, half of them with PhD positions, trying to understand every company individually and who could be the ideal potential partners, suppliers, and customers. Many of you know EPIC, many of you know that we organize a lot of events, that most important, we connect network. I want to strengthen this. Any of you who want to connect with any potential company, contact us, we'll make the connection. If you're looking for funding, we help you find the investment. We have now, listen to this, we have now the biggest website to find a job in photonics. The biggest website in the world to find a job in photonics is jobsinphotonics.com. We created it, and many of you know this because you're a EPIC member. You have access to a long list of market reports. Market data is freely available for all the members. We buy market reports from Joel, from Thematis, Strategies Unlimited, and we'll give them to you, so you have the access of this intelligence as a EPIC membership benefit. All of you who are not yet member of EPIC, please join us. We want to keep growing, want to do even better things than the ones that we are already doing. But I also would like to say that today is Integrated Photonics for non telecom applications. We have been organizing plenty of meetings on integrated photonics for transceivers, how they would enable for beyond 400G, a lot of telecom interest. But today we are going beyond that. We're going to know the interest of automotive, the interest of medical, the interest of laser industry, the interest of consumer. Let's see how we can do this. And we cannot do this without the support of our sponsors today. We have a lot, so I'm going to go very quickly through them. The first, we have IMS, a company, a great company for the automation of manufacturing of photonic integrated circuits. You're looking for equipment for packaging, equipment for testing of any module based on photonic integrated circuit. These people are great. They have great machinery, and they are actually also very specializing manufacturing for automotive industry. EVG, who doesn't know EVG? When it comes to semicon equipment, all the way from Austria, EVG is one of the market leaders in making micro optics and providing the equipment for the micro optics. Anything that you need for replication, these are the people to go to. Axetris, the micro optics revolution keeps growing. Axetris is a key company in manufacturing micro optics all the way in Switzerland. Not only the micro optics manufacturing, but also helping you integrating micro optics into any instrument. And of course, when it comes to packaging integrated photonics, they are very good on making the lenses that you need for the fiber to chip coupling. Jenoptik is an amazing company. We all know Jenoptik, fantastic equipment, but they are working for EPIC in developing a card for testing photonic integrated circuits. And you're gonna hear a bit about this during the meeting, because we are looking for pilot customers so they can work with Jenoptik on testing the integrated photonics from the testing center that they have at Jenoptik, the testing card they have at Jenoptik. OFS, when it comes to fibers, when it comes to fibers for telecom, but also specialty fiber for sensing and other applications. OFS is the key company to go. We are really happy to have OFS in EPIC. They have been helping many companies in developing prototype suitable to production of any specialty fiber, not only for telecom. Helia Photonics, all the way to from beautiful Scotland. Helia Photonics is a company that whenever you need any kind of coating or thin film deposition, these people know what they are doing. They are fantastic on making AR coatings. They are fantastic of actually making anything that you need on the facet of an integrated photonic chip. Who doesn't know ficonTEC? If you know photonic integrated circuits, you know ficonTEC no matter where you are all over the world. ficonTEC all the way from Aachen next to Bremen in Germany, they position themselves in the center of the supply chain of integrated photonics, and they are the one who are actually automating any process for packaging or testing of photonic integrated circuit. You need equipment for the automation of your packaging and testing. These people are the way to go. I'm really happy to have them at EPIC. And finally, Rockley Photonics. Rockley Photonics is a giant when it comes to photonics for datacom telecom, but their platform is suitable also for many other applications. They are looking for companies who want to be part of this platform, whether it is on the manufacturing or it is on the packaging. If you need a company that can go all the way to module and even instrument on a photonic integrated circuit, Rockley Photonics is the ideal partner. I went as fast as I could, and I cannot wait to give the floor to the EPIC specialist in photonic integrated circuit and also a very good friend of mine, Ana. Buona tarda. What's in the menu today?
Hi, Jose, and hello, everybody. Today in the menu is like I am waiting for a super delicious paella, and I just want to start. So here you can see this fantastic list of speakers. And well, today, as you can see, the talks are focused on applications and the latest developments in products based on photonic integrated circuits for sensing, of course, for medical, industrial, and transport applications. But also, we are going to have other companies attending, right, Jose? Yes, these companies are going to participate in all the discussion after the talks. So they are the entire supply chain for manufacturing of photonic integrated circuits. Yes, companies doing software, design houses, all kind of companies doing packaging, offering process and services, offering equipment, materials. Also, can you see what the amount of companies doing PIC modules for sensing? Or at least companies that are thinking about doing these PIC modules for sensing. This is why they're registered. So yes, we will find out in the next 2 hours. Also, of course, companies doing micro-optics components such as lasers, fiber components, R&D centers. Also, we have consultants. We have even an investor. And yes, well, and also, of course, all kind of foundries: silicon, nitride, silicon, photonics, indium phosphide, 3-5 components, polymer, and also even graphene foundries. And well, last but not least, ingredients for this paella, the European manufacturing pilot lines in photonics. So we have MedFab for manufacturing, testing, validation, and scale-up of new photonics technologies for the diagnostic field. We have Fabulous for the manufacturing of free-form micro-optics from prototype to pilot and large volume production. We have MIRFAB pilot line for prototyping and scaling up production of miniaturized chemicals sensors, and also JPICs pilot line for pilot production of indium phosphide PICs. And well, PICSAP. PICSAP is the pilot line for packaging and assembly of photonic integrated circuits. But well, we will be back to PICSAP in 1 minute, so I don't want to say anything else. Jose, back to you.
If any company is missing their logo in this slide, it's because you did not register to the meeting. This slide only includes the companies who registered for the EPIC meeting. If you want to be part of any future supply chains, please register for the meetings in time. And also I would like to say that if you didn't think your company was in the right position in the supply chain, or you have some comments about that, please give us the feedback. It is very hard to make these slides for every meeting, but we do our best. We do our best to know every company separately. If you have comments, please let us know. And also would like to say once more that this meeting is streamed online. So now I'm going to say hello to the people in YouTube. Hello, YouTubers in the world. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asoc.com, and I will be more than happy to make that introduction. This thing also goes for the people in the Zoom room. Please feel free to use the internal chat. After the meeting, we will have, of course, the one-to-one meetings for those people who want to do so. If you don't want to do so, it's okay. You want to do so, Susan Kermer, you can just send a private message to her. But most important, I think it's time to start. Anna, what do you say? Shall we start?
Yes, well, Jose, you always say that packaging is a bottleneck for the development of new products, right? Based on PICs. So in this context, a PICSAP pilot line has been working on developing standard processes that are compatible with large-scale production along the entire supply chain. So, well, PICSAP is the entire PIC ecosystem. And to talk about these services, we have here a special guest, Peter O'Brien, Director of PICSAP. So, Peter, if you want to start, the floor is yours.
Thanks, Anna. Can you hear me okay?
Yes, very well.
Yeah, very good. Okay, thanks, Anna. Thanks, Jose. And thanks for the opportunity to speak again today. We really appreciate the support of EPIC in promoting our pilot line. So I'm sure some of you are well aware of what we do in PICSAP. We've been running for about just over 3 years now. And I must say that when we started off, we really focused, due to the demand, on communication devices, so telecom, datacom type applications. But in the last year to 6 months, we've really seen sensors taking off. And essentially what PICSAP does is it works with companies, startups, medium-sized companies to large-scale multinationals all across the world. And now we're working with approximately 120 companies. And that's, as I say, a mix of early stage to quite large-scale companies. And in the last year, I would say sensors have really taken off for integrated photonics and the demand and the interest in that area. And essentially what PICSAP does is it works on the basic concept, helping companies move to early stage manufacturing. And it's not just ourselves. It's important to say that PICSAP is more than Tyndall. We have industry partners who we now work very closely with, and we have standardized packaging, what we call building blocks, and they're being developed into PDK, so process design kits. So when you lay out your device, you can design it such that it can be packaged with our building blocks. And really an important area that's growing for us is, we're talking to companies now looking at scaling up to thousands of parts, but very early on, companies need early stage prototypes. And rather than focus on expensive solutions, what we developed in the last couple of months is, as Anna's showing here, these generic packages, and these are prototype packages. And basically it covers a large range of requirements for users. So it's not something that you're going to productize, but it's something you're going to check your device to make sure it works well. You can look at the performance, you can look at the reliability to some degree, and test out the electrical interfaces and the optical interfaces. So you can see here we have fiber packaging, electrical packaging, and thermal management as well. So it's obviously very important. So these are now available, and if you want to evaluate these very, very quickly, it's possible. So the idea is rather than sitting down and designing a custom kind of proof of principle package, you design your chip such that it can be packaged with this. And as I say, the sensors area is really taking off. We have projects now for medical. So medical is really growing for us. We see fiber sensors on catheters for cardiovascular and guide wires. And they're particularly with a number of startups and large multinational companies. So that's a really growing area for us. Another area that seems to be taking off quite significantly is LiDAR. So we're working with a number of aerospace and automotive companies. So developing the solutions for different types of fiber sensing for medical and for sensing for LiDAR is really taking off. So again, appreciate the opportunity for Mana to speak today. And if you have any more questions, feel free to contact me.
It is one of the success stories of the European ecosystem to have PICs up. Today, you're saying that you want to talk to designers as early as possible so they can design the chip to fit the package. Where can they download the design rules? How can they have access to the design rules that they need to apply to their design to fit in their package?
Well, the best thing to do, Jose, is contact us. So we do have documentation, and for example, a lot of the design rules are in the synopsis PDK, but what I would suggest is they contact us. So if you go online, there's a phone number, there's also an email, you will get an instant response. So please don't hesitate to contact us. We'll help you through that process. And we have a team in Tyndall in what we call our gateway, and they will work with you. I think the feedback from early stage kind of contact has always been very positive. So we'll give you advice. And if we can't help you, we will make recommendations on someone who can.
For EPIC, it's very important that we don't organize conference, but organize meetings in which people can follow up. Today, Peter, you have a lot of companies who want to interact further with you present here at the meeting. Anna, you forgot to say this, 180 companies registered for the meeting today. They want to do business in photonic integrated circuit for sensing. Peter, thank you very much for being with us this afternoon. Stay tuned. There will be quite a lot of Q&A for you afterwards. But now I want to go to Anna Nikiel, who leads business development at Technobis in Almar. Anna, what's new with you in the field of integrated photonic sensing?
Hello, hi, thank you, Jose. And let me say that I'm delighted that this meeting are bringing in so many end users in our discussion. And now I'm gonna share my screen, what probably will be not so easy.
Technobis has been one of the pioneers of being in photonic integrated circuits for sensing. Actually, the CEO of Technobis, Pimcat, was for many the biggest innovator in industrialization of integrated photonics. Anna, if you go to full screen, that's perfect. The floor and the attention of everyone goes to Technobis. Goes to you, Anna.
Oh, wait a moment. I think that I have to switch the screen to the presenter view. And now, do you see the full screen of the slides? It's
crystal
okay?
Clear.
Okay, super. So yes, thank you, Jose, once again, and let me start the story about the Technobis. So Technobis has been designing and making next generation sensors since 1996. We built our reputation by responding to the challenges that come directly from the end users. They want to detect the things that have been difficult or impossible to detect so far. And we knew that only cost-efficient way to scale this demand was to build a complete system on the photonic integrated circuit. So here are some ideas we are working on. Fiber optic sensors on the chip are a huge step forward. They are small, lightweight, inert to the chemical substance, and able to withstand high temperature under danger condition. Think, for example, of oil and gas platform or measuring temperature inside an MRI scanner. The sensor must be immune to the electromagnetic interference. And our ability to monitor pressure and shape has many new medical applications. Most sensor detection devices, so-called interrogator, use free space spectrometry. Free space means that in the measuring the reflection, the light will move through air. But this approach to the spectroscopic analysis have a fundamental limits. So devices are often bulky, and there are limits to the resolution measurements, accuracy, and power consumption. So the goal is to replace traditional discrete micro-optics components by the complete system on the chip. These PICs are key to substantial cost reduction as well as a standardization of the specification and processes. Together with our strategic partners, we are currently focused on bringing novel type of the strain, temperature, and pressure sensor to 4 markets. In medical, we are developing RF MRI temperature sensing, and we think that fiber optic shape sensing has a great potential for the several medical related application. For instance, to sense curvature and shape in both 2D and 3D. In the automotive sector, we are active in the battery condition monitoring as well as downforce and vibration measurement. In aerospace and new space, Technobis is looking to expand our expertise in overheating detection and prevention maintain monitoring. And we are specialists in the high dynamic strain and temperature monitoring in production processes. And let me quickly highlight one specific example which that Jose has asked me to talk about. One of the many challenges in the endoscopy is that the surgeon is not in the direct contact with the tissue. So he or she doesn't know how tight to grip. If it's too tight, then a healthy tissue gets damaged, which is not what we wanted. And haptic feedback is the solution. This is already known in the game controls, and haptic feedback recreate the sensation of touch. This helps the surgeon to feel the level of force being applied without having to look at another screen. In vivo experiment that we done with this tool make it possible to feel the heartbeat in the blood vessel through the handlebar controller. And this is also a device which is very easy to use. The feedback on our haptic feedback grip from oncologists has been also extremely positive. They can operate on more vulnerable, risky tissues such as cancerous tumors. Minimally invasive oncological operation will reduce the need for open surgery with larger incisions. And cardiovascular surgeon can clearly feel the difference between vein and artery. We believe the fiber optic sensing lead to more accurate operation and faster patient recovery. And I'm personally very excited about this sensor. I have also one more piece of news from Alkmaar. We are just installing some new tools in our PIC packaging foundry. So as well as packaging nearly 300 PIC designs for our own products, we can offer a wealth of PIC packaging expertise to external clients. Everyone knows that this part of the process is often the major cost factor, and the requalification can be a serious roadblock to commercial success if you don't get it right. So I hope that explain what we can do for the EPIC members, and maybe there are companies in the Zoom room who can use our sensor, packaging and testing expertise to quickly launch products that their clients need now. If so, I'm happy to follow up. And thank you for your attention this afternoon. And it's perfect 6 minutes, so I'm very happy.
Yes, thank you very much, Anna, for a great presentation, as always. So please tell us, okay, you already said what can the members of EPIC do for you, but maybe you can tell us about a specific challenge for packaging that you could have. So yes, we can try to find for you a collaboration here.
Yeah, so as we say, we scaling up with our packaging capability with big help of Tyndall Institute with picks up pilot lines. And we have at this moment 2 lines. One is focused more on the prototyping and doing like a first approach for the packaging, and the second line is more focused for the scaling up. And of course, we still increasing our capabilities and still investing in our machinery and equipment. And of course, we are looking for the partners which are going to help us to learn more about the packaging. So we still, this is a learning curve. So we learning from our clients and our clients learning from us. And we're very open for all kind of the collaboration in the respect of the packaging PIC. Because as Jose always repeat, I have to completely agree with that. This is one of the major costs of the PIC bringing to the models at the moment. So we all working very hard to bring some standards and to reduce the cost of the packaging, and also what is important, reduce the time.
Okay, so for these companies in the room able to provide Technobis with these capabilities, just send me an email and I will contact you with Anna. And well, you know, regarding benefits of photonic integrated circuits, we have a company in the room that is a new company for our ecosystem, Jenoptik, Axel. Hello, Axel. Yes, you are looking at me. Hello. Would you like to unmute yourself and talk about what is what kind of interferometry you are offering, and well, what kind of fiber sensors you are offering?
Do you hear me now? Hello.
Yes, very well.
Jenoptik is in South Switzerland. No, I have a meeting with Anna at 5 o'clock, but my idea, I will repeat the same question later on, is that you are talking all of back grating sensors for medical applications. My question is, are you familiar with white light interferometric sensors, where actually I would say that in medical applications are much more used than back gratings today? Are you familiar with them?
Yeah, we are familiar. We have our devices are more focused on the FPG systems, but of course we, our R&D teams working on the different kind of the interferometry and exploring the new areas. But I understand. White light is much more useful for the medical application. However, our application for the shape reconstruction or for this haptic feedback, which I show, is also working very well.
And is there any product in your pipeline coming out?
Many, which I think that I have to wait a little bit to make the announcement. But we're working. I don't know how much you are familiar with Technobis, but I think that we all agree that our company is known from being very experienced with doing R&D and making the products which are everybody say that are impossible to do. So we are working for the very interesting products, which we hope very soon came to the market in medical area, but not only in the medical area. Yeah.
Okay, thank you. We will continue our talk at 5 o'clock.
With pleasure.
Thank you.
Remember that anybody who wants to continue the talks at 5 o'clock, all you have to do is send a private message to Suzette Germer. She's setting the one-to-one meetings. And don't stay too long, because last time we finished quite late as well. So let's read the YouTube. The YouTubers on the wall are asking questions. We have a first question for Peter O'Brien. The question is from Jan Vermeeren from KLST in the Netherlands. Peter, they are wondering what is the business model behind PICs?
Well, the main business model is to support companies grow their manufacturing in Europe. So we got funding originally from the European Commission, and we're supporting companies. We transfer that to our industrial partners. So Tyndall, for example, has its gateway. Beyond the 4 years of the European funding program, we support the early stage high risk development activities, and the companies pay for that. and then we transfer it across to our industrial partners for scale up. So we do not want to be involved in the manufacturing. We want to support the development. I think that's very, very important. So that business model is working very well. I should also add that we support that business by training. So we charge people for training. And just a final point, it's worth mentioning, we're moving now to a 3D virtual reality training program. It's kind of a mix between the hands-on, where we bring people in, and online. So training and the high-risk technical development, and then transfer to our industrial partners for scale-up.
It is one of the biggest industrial push I have seen for photonic integrated circuits, and I already heard from you and Anna that in the coming weeks you're going to have a full list of pricing for the packaging of photonic devices using the standard package you present in the presentation. That's a huge leap in industrialization. So on behalf of the European ecosystem, congratulations, Peter. Keep going like that. Anna Nikiel from Technobis, the next question comes to you. We're wondering, how do you solve the problem of temperature control at the FVG level and at the PIC level?
Yeah, so one of our strong point in Technobis is our thermo managing. So because we have years of the experience where we package our own PICs, we are also very good with thermo managing. And yeah, I know that there's many companies which working now specifically on this task. We have some collaboration, but this is something what we figure out with starting from the console analysis and simulation, and finish for the very practical solution. Yeah, I think that this is one of the strong point of Technobis is the thermo management. So yeah, if you want to learn more, we are happy to support the companies which need help with this.
I think many companies need help with this. I would like to first of all congratulate you the haptic feedback. The PlayStation 5 is coming in a couple of weeks, and I already know that the controller includes haptic feedback. The future of haptic feedback is in consumer electronics, and that's why I was very passionate on having this presentation from you to start the meeting, because I do believe this is a huge market. We started with medical, we go to consumer, and this is what we want to go for photonic integrated circuits for sensing. There's a lot of questions in the chat, but there is a lot of Q&A. So I'm going to address the questions afterwards, especially the one on biosensing from Peter Hasmouth. Stay tuned, because we're going to have a lot of discussion about this. But we continue. We go to one of the companies who's making a big difference on the LiDAR industry. We go to Omnitron Sensors. I had the pleasure of announcing the CEO, co-founder, and one of the most successful young entrepreneurs in the EPIC network, Eric Aguilar. Eric, tell us about LiDAR. Tell us about how we can help you. The floor and the attention of everyone is yours.
Great. Thank you, Jose. Thank you for introducing me. Really appreciate it. Can you guys hear me okay?
Loud and clear. It is 3:30 in the Netherlands. What time is it over there?
It is 6:30 in the morning over
Fantastic.
here. A little early. Kids are getting up, so you might hear some background noise. Let me share my screen here. All right. Let me see. Can you guys see this okay? Great. Awesome. Hold on, I have to move monitors back and forth. Okay, so hi, I'm Eric Aguilar. Thank you, EPIC, for hosting me. Really appreciate the opportunity to present our view on LiDAR products. And today I'm going to be specifically focusing on our photonics integrated circuits for the LiDAR product that we are developing. So as Jose mentioned, let me see if it's going, there it goes. I come from a background developing and integrating sensors for robotics applications. I've worked at Google X, Tesla, and Argo AI as a leader in sensor products. Now, while working at these leading companies looking to unlock self-driving, I noticed how critical LiDAR is along with its issues. Primarily, the biggest problem that I'm seeing is not in building these things, but in the durability. They last less than 6 months, and they fail due to the car shaking and the sensor baking in the sun. And if any of you guys know, photonics integrated circuits and free space optics are opposed to each other. As soon as you start going into the air, the problem gets exponentially more difficult. Not only the issue being that they're unreliable, but when they fail, the car can no longer drive autonomously. These are the most important sensors to seeing the world. They're also expensive. So each one of them are expensive, but when you look at a fleet of them, a small fleet, of robotaxis, you're actually spending hundreds of millions of dollars on these sensors. And the reason for this is that there's the current limitation to how they're manufactured. So let me give you some background and context here. LiDAR for navigation, and I want to be specific here, for navigation purposes, requires active alignment in order to preserve beam collimation. So in other words, you need to have a beam that's only a few millimeters in diameter as it goes hundreds of meters in range. This active alignment is the current bottleneck in cost and reliability because it requires the use of micromanipulators to align the laser to the substrate one channel at a time. When you look at a LiDAR with hundreds of channels, you can quickly see how this is time-consuming and expensive. The laser is also prone to losing alignment due to the constant vibration and temperature cycles the LiDAR experiences. This results in costly repairs to realign the laser with the optics. So this is where photonics integrated circuits have a huge potential to disrupt the market. With that, we've seen that today's process steps have reached their limitations, and this industry has been flat for more than 10 years. We're adding a new degree of freedom to design with, and this is the big deal of what we're working on. With that, we can reduce the cost of LiDAR by 100 times. We can improve performance of MEMS. So MEMS stands for microelectrical mechanical systems by 10x, and improve reliability from months to years. So how are we doing that, and how can you guys help? So it's like going from 2 dimensions to 3 dimensions. Omnitron can build structures that were previously impossible to get around. We can now address the engineering challenges such as the ones facing LiDAR. To go a little deeper into what's going on, you have to understand that the current limitations to MEMS structures have been limited to this aspect ratio of 10 to 1. So if you look at this image here, you can see that in production today, the latest technology has about a 25 micron depth with a 2.5 micron gap. For context, this is about 100 times thinner than a human hair. This is where the latest technology is in terms of scanning devices and steering devices. So what are we doing? So with a higher aspect ratio, we can do in a manufacturing process, we're able to close the loop on an optical scanner by providing the ability to measure the position of the mirror. So this allows us to provide a system that can inherently deal with the dynamic environment in the automotive and robotics applications that experience constant vibration and temperature change. We can also reduce the drive voltage by an order of magnitude to reduce the cost and improve electronics reliability. So if you're familiar with MEMS systems, in most cases, it takes hundreds of volts to move this thing. We can now reduce this to tens of volts, which is something you can do in an ASIC. So let me see. Okay. So another big thing that we're doing is moving away from using micromanipulators to align the laser with the remaining of the optics, and we're moving to batch level wafer processing, and we're able to eliminate this active alignment step altogether. Instead of aligning one element at a time using epoxy, we're able to use wafer bonding techniques to align the laser, the lens, and the mirror with the robust proprietary fabrication techniques. This, in turn, allows us to create the step change needed in LiDAR. So what we're doing is not building a LiDAR at the end of the day. We are providing a critical component to the LiDAR industry. So if you look at the LiDAR landscape, you have very expensive 100,000 plus units that are high performance at one end of the spectrum, and you have single channel, slow range systems at the other end of the spectrum costing less than $100. With our IP, we can service these companies and create the step change needed to build reliable, high performance, low cost LiDAR solutions. To do this, though, we need to build new photonics integrated components like the ones offered by Omnitron. So hopefully you got a chance to learn a little bit about the challenges facing LiDAR. This also aligns with what Elon Musk said about LiDAR, as many of you are aware. in that they are expensive and unreliable. Omnitron is taking on that challenge to build the next generation of photonics integrated circuits to address the demands of the robotics and automotive market. Please feel free to reach out to me to explore opportunities for partnerships. We need help in every aspect, from packaging to wafer level bonding techniques to aligning lasers with lenses. We're in the process of fabricating our mirror with a local foundry. We're looking to expand that to a large scale foundry because we need to reach volume, and really looking forward to collaborating with this community to grow our business. So thank you.
Thank you very much, Eric. Very nice presentation. Okay, so then, what are the challenges that you are facing now? How can we help you? So what kind, I don't know, do you need a new foundry? Do you need a new packaging service, a new machine? We have everything. So how can we help you?
We have a good partnership with a local foundry, and we selected them particularly because they have the tools and processes that can scale. So we can take the recipe that we're building at the local foundry and go to one of these large scale foundries. Without violating NDAs, what we need to do is get connected to some of these larger scale foundries so we can move away to these limited capabilities in terms of volume with this foundry. But wafer bonding is really important to us. So wafer bonding glass to silicon, wafer bonding lasers to our mirror. That is very, very important to us. So we are looking for help in that aspect. And then at the end of the day, packaging, just like Jose, you mentioned, packaging is super, super critical to optics. So working with a foundry or a company that can do not just small scale prototype packaging, but is able to, the key being able to scale that up quickly. So how do we build something that early on allows us to experiment with, but then are able to scale up to mass production? Because the big thing here is not building one or two of these things or a few handful. It's building thousands of these in a quick, cost-effective way. So those are the things that I'm looking for.
Okay, yes, I'm sure we can help you. So, and we have now two questions here. So the first one, Douwe, would you like to make Douwe from Leisching, would you like to make the question?
Okay, yeah. So how do you see photonic integrated circuit technology fit your MEMS platform?
Oh, well, it's a fewfold. One, definitely the laser and the laser source that we're selecting. We have a good idea of what we want to go with for our initial offering. But going to, for example, looking at 1550 nanometer wavelength technology and how we integrate that with our optics in our mirror is super critical to understanding that better. There's a lot of details there that we need help with for sure. So definitely the laser source, how it's collimated, coming out of the silicon versus what we need to do with the lens is really critical for us.
Okay, thank you. And we have also a question from Peter. Peter, would you like to make the question?
Sure. Hi, Eric. Very interesting presentation. Just curious on the wafer bonding process with the laser. I see it looks from your drawing that you're coming out of plane of the waveguide. So it's kind of like orthogonal to the plane of the optics, if you will, or maybe I misinterpret your diagram. But that bonding process, how's that achieved? Or is there temperature a big issue in that?
Yeah, you bring up a very good point. We are looking at using eutectic bonding to bond so we are using a VCSEL for our first generation product, which is an out of plane. The laser is orthogonal to the surface in our approach. But yeah, the approach that we are looking to use is eutectic bonding for sure. But you are absolutely right. How do you survive the temperature cycle that you're going to go through in that bonding technique to make sure the devices don't fail? You're absolutely right. It's as I've been saying, like building one or two of these is easy. It's when you got to try to do this and deal with achieving high yield that it becomes really hard. And that's where these temperature cycles are really important to address.
Okay, thanks, very good.
Okay, and we can try, because we have here Lepin Heiko from Continental. Lepin, hello, how are you?
Hi, how are you?
Hello, very good to have you here. So maybe, well, you know, we had a discussion like 2 weeks ago about the use of photonic integrated circuits in LiDAR, no, for automotive, miniaturized automotive LiDAR. What do you think? What is the vision of Continental for the future of these technologies?
Oh, we work on several different paths and to explore what's possible in the future, and we are definitely looking into photonic integrated circuits. And but what we see, and it has been mentioned in earlier talks already, the packaging becomes a major contributor to cost. Now, we see this in today's technology, and we will see this in future technologies as well. The smaller the structures, the more need for hermeticity or semi-hermeticity. And suddenly the packages grow expensive. And I'd be interested from any of the participants here, what's your view on a let's say reasonable packaging technology for photonic integrated circuits and micro electromechanical systems?
So,
Okay.
so this, Anna, hi, can I answer that question? I can't wait to answer it.
Please.
Yeah, no, it's really interesting. Thanks. Because I think the issue of cost is a big problem here, not just the assembly process. What we're looking now at towards is surface mount. So really surface mount type packages where everything's done at wafer level, and you pretty much have like pick and place, like in the electronics world, with machine vision systems on a PCB type assembly. So micro optics are integrated into the package, hermetically sealed, and you have an interposer where you connect between the electronic chip in the surface mount package and the photonic device. It's hermetically sealed, it can be, and it can be done at a wafer level. And the cost potentially, looking at the process here, can be an order of magnitude. And the assembly times can be significantly reduced. So I think surface mount type packages are really the way forward here. That's we've started a program around that. And I think it's shown its merit in the electronics world. It's the de facto type package, like a ball grid array, and it has to be solder reflow compatible. So that's where we're really kind of starting to develop up capabilities there.
That's actually really good to hear. And I totally agree with you in terms of the sensitivity in packaging, especially when it comes to hermeticity. Moving to wafer level process steps allows you to significantly reduce the cost and improve yield and volume. So going to that level and then getting away from this active alignment step that is so cost prohibitive today, and the current bottleneck is what's really key. So you're absolutely right, is to try to build a submodule that at the end of the day, you simply use a pick and place machine to assemble it on a PCB. That is right on in terms of what you need for the automotive market.
Yep.
Okay, so thank you very much. Well, we have another question. Greg from Rockley Photonics. Greg, would you like to make the question by yourself?
Greg from ficonTEC service, you mean?
Ah, okay, so we didn't name you very well.
Oh,
sorry.
yeah,
Now I'm going to
okay.
change the name of your company.
That's okay.
And you weren't without the camera, sorry. So please go ahead with your question.
No problem. Eric, a question about your wafer level assembly. Are we looking at singulation into single devices, or are we also looking at chunks of MEMS used as arrays? And what does that mean for your testing requirements?
Oh, yeah. So I'm very familiar with that. Well, my co-founder is much more familiar with that, with doing optical-based switches for the telecom industry, where you're doing many mirrors at the wafer level and dealing with that. We do have a customer interested in that. My son is joining us for this meeting. He may have some input for these answers. But I was going to say about that. We do have a couple customers asking for a mirror array to then. Hold on a second.
Okay, Eric, thank you very much for answering.
Yeah.
Yes, that was.
So anyways, as I was saying, we do have customers asking for an array, and we are looking at building an array as well with some offset in the mirrors. So in other words, you have one mirror that's looking forward, one mirror that's looking off by 30 degrees or so, and the other one same way to cover the field of view. That isn't our first generation approach because that adds a significantly higher level of complexity. And as one of my mentors said, invent one thing at a time. But we are looking at that for our next generation to do an array.
Eric,
Okay.
first of all, there's a
Thank
question
you.
here in the chat from Fred. I'm not going to read it because I want you to answer it offline, but they are proposing a phase array solution for your chips from Wave Optics, from Vario Optics. I also would like to say that we have companies who are automotive qualified, like SUS Micro Optics in Switzerland, developing micro optics for the packaging of chips, and they should talk to you. There are many, many connections. It is great to have a company like Omnitron in EPIC. Thank you very much for supporting the association. I think it's time to move on. Let's continue with this amazing program, and let's continue with this fantastic agenda. The next presentation, third presentation today, we go to the consumer market. I'm very excited about this. We go to a company that everybody knows because many of you have seen it in your kitchen, Electrolux. Cristina, thank you very much for being with us this beautiful afternoon. Grazie mille. The floor and the attention of everyone, now more than ever, goes to the kitchen and goes to Electrolux. The floor is yours. I think Cristina is with us.
Yes.
Yes, there
Hello.
she is. Thank you very much for joining.
Thank you very much. I'm going now to share my presentation. Just a second. Please let me know when you see it.
Yeah, you can go to presentation mode. Yes.
Yeah. Okay. Okay. So hello everyone, and thank you to the EPIC Association for inviting me to present at this online technology meeting on Photonic Integrated Circuits for sensing applications. My name is Cristina Bertoni. I'm from Electrolux, from the R&D center of Electrolux, located in the northeast of Italy. And I'll talk to you about opportunities for mid-infrared gas chemical sensing in the home appliance industry. Electrolux is a global leader in kitchen appliances, as already announced, including preparation, storage, and dishwashing. The group has 47 factories on all continents, sells in 120 markets, employs about 49,000 people, and has a wide product portfolio in both the household and professional sectors. Company priorities have been reviewed according to the next normal that is taking place after the COVID outbreak. While a strong focus is kept on health and safety measures for all employees at the workplace, strong priorities raised by the pandemic are to reorganize the supply chain, to accelerate time to market of prioritized projects, to boost cross-functional teamwork. In any case, Electrolux remains committed to its science-based climate targets for 2025 and to become climate neutral along the value chain by 2050, in alignment with the Paris Agreement to keep global warming well below 2 degrees C. Concerning product development, in the last decades, Electrolux made its transformation from a typical manufacturing company to consumer insight-driven company. In line with this transformation, addressing drivers and trends in our offering is imperative because the transformation from a typical manufacturing company to a consumer insight company implies the need to capture prevailing trends and tune products and service offering. Now, product and services offering will be tuned to the new normal, to new hygiene practices, to online shopping, to reduction in incomes, to the quest for trusted brands, for digital services by keeping a strong commitment to sustainability. pandemic increased the time spent at home. Here you can see a plot for via Google mobility trends, and data related to residential revealed that there was a surge in time spent at home when the outbreak happened, and now we are still at around plus 10% time spent at home in the UK, and this is something that we can see happening everywhere. Indoor well-being is determined by indoor environmental quality, which in turn encompasses different parameters like air quality, sound quality, odor, and light. So air quality at home is as important as other parameters that you can see depicted here below, such as energy usage and generation, heating equipment, performances, and water usage. So this is one of the domains where we are actively working. In particular, regarding air quality sensing, I here report a table with targets that are both gases and particulate as well, but this is actual targets in this domain for us, and applications for gas sensors in indoor safety, like early fire detection or the detection of poisonous gases, in health and well-being, that is CO2 monitoring, or the 6 building syndrome, where some, let's say, poisonous gases are present, and we need to detect them in order to alert at least the user about their presence. And also efficiency, like, for instance, the noise produced by air ventilation or circulation systems. So by reducing air circulation below certain parameters, we can allow reduced noise, so a better sound quality or sound environment. In any case, requirements for gas sensing indoor are the 3S criteria: sensitivity, selectivity, and stability. Sensitivity, of course, from some gases in particular starts from ppb, parts per billion. We also, by addressing health and safety, we certainly need to classify hazardous versus odorants in order to provide a good information to the user. And the reliability over the time, as one said before, is of paramount importance to us. We need also fast response and recovery, of course, and lifetime and maintenance is also two topics that comes along with this type of target application. We entered the MIRFAB consortium in 2019 as an end user, and here you can see a picture of some of the partners gathering in our site in northeast of Italy for one of the periodic meeting in 2019. It was a very nice meeting where we could appreciate modules and devices developed by the consortium partners. And we are about to receive a module this week, actually, from one of the partners we are collaborating with. They send to us already the characteristics that you see here below. Of course, the gas target cannot be seen for confidential reasons, of course, but we are really happy and looking forward to characterize this module for the target application. Within this project, in any case, we worked in the lab to collect information on interference that could affect the sensor response along operation. We provided the specifications, or helped defining specifications, by providing a mid-infrared spectrum of the target gas mixture, which was important for the supplier, so to define the wave numbers at which it was best to let the module work. The mid-infrared module that we are about to receive will be characterized at our labs in operational conditions of interest for the final application. And we also, let's say, presented, in any case, this work internally by emphasizing the technology roadmap for mid-infrared optic devices miniaturization, which could enable in the near future large-scale, low-cost devices that, of course, are of strong interest to Electrolux. So I would like to thank you for your attention, and please, if you have any question, I'm here to answer as much as I can.
Thank you very much, Cristina. We are so happy with Electrolux MIRFAB. MIRFAB, which is the pilot line for prototyping and scale-up volumes of miniaturized mid-infrared sensors. So, Cristina, so now Electrolux is exploring the idea of introducing photonic integrated circuits in their product. So now in MIRFAB, you are developing this product that is for air analysis, right?
Yes.
Which other kind of applications, which other kind of collaborations would you like to explore in the world of photonic integrated circuits? I don't know, for washing machines or for, I don't know, for any other kind of applications?
Well, let's say that the domain of air sensing is very broad because it's not actually only indoor air quality sensing, but there are several appliances that could benefit from gas chemical sensing. And typically, these are gas targets that are related to phenomena that are very difficult to detect. For instance, the development of fungi or molds that leads to odors that are not nice for the final user. And so this is, as a matter of fact, something that is more related to the appliance than has an effect on the environment as well. But the smell could be an issue that regards also other appliances like the refrigerator or the dishwasher. It depends really, if it is, it depends on the habits as well of the user. So the discussion here is even more complex. And as a matter of fact, I stress that I belong to a team that is working on sensors within an artificial intelligence perspective. So sorry about that. There is a phone ringing just now, but sorry, just a second.
No, don't worry. Okay, because we can follow. We have here also other partners of MIRFAB that maybe would like also to comment. So, for example, Jennifer from QuantaRed. Hello, Jennifer.
Hello, sorry.
Hello,
my colleague just asked me something. I didn't hear your question.
No, I mean that I was explaining the people in the room that we have other partners from MIRFAB here. So yes. Maybe would you like to explain what is the role of QuantaRed in MIRFAB and what kind of sensors based on PIC are you developing?
Yes, actually I'm not directly involved with the MIRFAB project, but I know from my colleague that we are also another end user, and we are testing different components from different partners in the consortium, like I think Fraunhofer is also in the project, which I saw on the screen that you showed before. So we are testing all the nice things that the other partners are providing and see if they are even better than we are expecting that they would be.
Okay, thank you very much, Jennifer. Okay, so there are any question, any other comment for Cristina? Because you heard she would like to have other collaborations for developing other kind of PIC-based products to put in the fridges. I need one of these fridges. So okay, so if there are no more questions, yes, let's move ahead in the program. Okay, so next presentation is for Patrick Leisching from TOPTICA. That I hope you are here, Patrick.
Yes. Hi. Good afternoon.
Very good. So will you mind to share your screen? And
yeah, just a second. So hello, everybody. I hope you can hear me and see my screen.
Yes, very well.
Okay, good. So my name is Patrick Leisching. I'm the head of R&D from TOPTICA Photonics. And thanks for the invitation to present what we are doing on PICs, why we are doing, and what we want to discuss in the future with our partners. So this is just a snapshot. Please don't hesitate to ask any question. We have plenty of material. So what is TOPTICA Photonics? To give you an idea, we are now a team of about 320 worldwide, which is no longer a small medium enterprise, but a medium enterprise. Our revenue is up to 75 million. Even in this Corona year, we are very proud to announce that we are, well, we got some hit, but not severe, no severe impact from the Corona crisis, and we continue to grow over the next year. This is for sure. So yeah. Future is bright for us. What is our technology? We do diode laser systems, we do ultra-fast laser systems, terahertz systems, and high-power laser diodes. And here the PIC comes into place for the diode laser systems. This is an interesting challenge if you use several diode laser systems and want to have some sort of optical ASIC system. Well, what did I pick out? We, from a market point of view, we work in quantum technologies and biophotonics and in materials, meaning non-destructive testing. So in the materials here, in the non-destructive testing and in the quantum technologies, you need an optical isolator. So it's some sort of a problem. So we started first in the biophotonics area where the optical isolator is not needed if you use a PIC with a diode laser system. So here in the right-hand corner, you see what is how biophotonic is made of. You have some molecules, some interesting material, tissue material, and here are the wavelengths where all the microscopy, the flow cytometry is working on. It is between 500 and 670, and at the end of the day, this is more or less the products TOPTICA has in the shop. You have diode lasers starting at 375, which go up to 785. And the output power of these diode lasers is between, let's say, 50 up to some 100. So a big question is, can we make it small? The boxes today have the size of a shoebox. And what is the best thing to look for? The mass application. And the mass application here in this area is 1,000 units per year, not a million or so. So when we speak of PICs, we have these sort of wavelengths here, 405, 488, 561, and so on. And this is the 90% market out of this wavelength shop here. However, you need to address all wavelengths. Then PICs, you see here in the UV, I have no hope that a PIC would be able to carry and transport 300 milliwatts of 405, but the 25 milliwatts, why not? And there's a lot of applications which need a 25 milliwatt laser machine only. So what target applications did we look for? This is from our PICs for Life project together with our partners. We looked for a confocal fluorescence microscopy for a lab-on-a-chip solution and for a flow cytometry use case where we are going to go for point of care. What means lab-on-a-chip? Then this sort of system here could be done for 10,000 euro and could be in a doctor's office. And here in the flow cytometry, if you shrink this flow cytometer, you could imagine that a doctor has a carry-on package to test the blood of a patient. So how does it look like? The typical problem is always the same. You have laser diodes, 640, 561, 488, and 405. And somehow you need to combine all these wavelengths in one single fiber. So if you look from a logical point of view, you have here variable optical attenuation, you have a wavelength combiner, and you have here some sort of coupling device to the fiber. And if you look from a practical point of view, this is what the design engineers have made out of it. This is a PIC here, Photonic Integrated Circuit. You see here the different wavelengths. And the challenge here really is the span. You have a span between 640 and 561. and you need to make sure that by some magic ways, all of these wavelengths end up in the same waveguide and finally are coupled into the fiber. Does it work? Yes, it does. Here's a first prototype from Leisching, and what you see is we are mounting the prototype, we are testing the prototype, and it's much more impressive to see it with light on. Light on looks like this. So here you see we couple into the fiber, we couple into the waveguide. In the waveguide, you see the propagation of the light here. This is scattering, and at the end of the day, you go out from the waveguide here, and you see here the wonderful colored picture out of this beautiful PIC. And as said, the challenge here is the widespan between 405 to 640, and we are more than happy to look for partners to explore the future of these applications. Thanks a lot.
Thank you very much, Patrick, for this, because this makes me extremely excited. We've been always trying to get to add functionality to laser systems, because as many of you know, laser technology is by far the biggest application field of the EPIC members. So Patrick, this is the EPIC question. You have the entire supply chain in front of you. What can they do for you, and what could you do for them?
Well, from a supply chain point of view, what we need is gallium nitride laser diodes. So this is definitely a challenge. Yeah, you can buy a Nikiel laser diode, you can open the package and work on the Nikiel laser diode, but it's not a clever idea. I guess Europe needs a gallium nitride fab. This is what most wanted from not a one more quantum computer, but one more gallium nitride fab in Europe would be nice.
Yeah. Sorry, I just have to confirm that if we're talking with our clients, that this request it's back.
Yeah. we are actually seeing that for any customized growth of gallium nitride. Actually, we do have potential players here, so please let us know. I can already tell you that we are working with Tampere University of Technology to actually do customized growth of gallium nitride for different applications. So you have a certain wavelength targeted, we can make the first prototype in EPIC. So that is great. But Patrick, you saw the presentation from Electrolux. That was very interesting, but they are looking at the mid-infrared wavelength band. And then Greg from ficonTEC posted, the price here, it could be expensive. For many years, I've been dreaming of having a cost-effective supercontinuum laser. And the only way to make this cost-effective, and John from OFS is smiling, is to remove the fiber. So I wonder, is there a way to use these very low-loss silicon nitride chips that you've been using from Leisching, from Leisching to actually make this extra cavity outside and make a supercontinuum generation on chip?
Yeah, we already have done. We have used a gallium nitride waveguide from Leisching and generated a supercontinuum. Done. It's easy. You can. However, you still need the fiber laser as a seed or so, but a fiber laser by principle is not expensive. It's just a question how many of these fiber lasers would I produce every year. But yes, it's doable. And there's a publication from TOPTICA with a Leisching PIC where we showed how good or how bad you can generate a continuum.
Fantastic. I am very happy that you're working already with Leisching on this, and we have another potential partner for you. Matthew Curry from Brodex has a question. Matt, thank you for joining. What's on your mind?
Hello, Jose. Can you hear me?
Loud and clear.
Brilliant. Thanks, Patrick. That was very interesting. I work for a company that makes silicon PLCs, basically. And I wonder if you could use a single AWG to do your multiplexing instead of these multiple wavelength combiners.
But it's the same or not? I come from telecommunication, and AWG is if I just go back to the picture here, it's a 4-color AWG, which I'm using here. And in telecommunication, you have 128 color AWG. Spacing is a nanometer apart. And here I have a spacing of 50 or 100 nanometers.
Right.
It's one piece of silica I'm using. It's just so that the spacing of the wavelengths is, well, 50 to 100 nanometer.
I see. So you're using these separated wavelength combiners just to get around the fact that you have a large separation.
Just a second. Yeah, it's just, I need to, here. what you see here is you have a wavelength combiner, one more. I don't know how you can calculate what you want to calculate, but at the end of the day, this is a simple 4-color WDM, like in the 90s in the telecom, where you combined 4 wavelengths, 10 or 20 nanometer.
Patrick, how much
yes,
power?
How much
do you have some limitations on the power you can put through the EWG?
Yes, here the limitation.
We are not seeing the slides. You are.
Okay, sorry. So here. Time. Okay, sorry. This is the picture here. This is the logical scheme of a 4-color WDM multiplexer. You have 4 colors in and one fiber or one position out here, and the limitation clearly is the power. So with the red light or the yellow light, you would not burn the facet here, but the 4 or 5 nanometer easily burns the facet here. And what you would do is an end cap. If you end cap this waveguide here, you can couple in maybe 100 milliwatt or so, but certainly not 300. So, but 100 milliwatt anyway would be good enough. And then if it comes down to the photon efficiency, the one thing is you feed in a photon here. How many photons come out here? If you do this by a PIC, you get a 25% in to out. And if you do it in a macroscopic optical arrangement, micro optics, you would get 50%. So this sort of PIC introduces a 3 dB loss compared to a macroscopic setup. But here, I guess, clearly 4 or 5. If you think of PICs, then this facet here will be burned if the power is too high.
See, but with the so we can make AWGs with silica glass, so those can handle up to about 500 milliwatts at 1550. That is, obviously with 405 it would scale, but perhaps it's worth us opening a discussion about that as well.
Yeah, but you need the waveguide. Oh, the thing is, we made our choice for silicon nitride as the absorption starts at 370 or so. So the first thing is you burn the facet. The second topic is more or less the scattering in the waveguide, and the number 3 loss is the absorption. And 405 is in all cases critical. You have the facet here, you have the scattering at the waveguide, and you have the absorption in the material. So yes, of course, if you have a better material than silicon nitride, we are more than happy to see if it's working or not.
Sounds good.
Patrick, it's an honor to have you here in the room. It is really great to see how the industry of integrated photonics is actually connecting with other more mature photonic industries, and TOPTICA is one of our key members in quantum technologies. There is another potential panel for you with a question. Ruth from Multiphoton Optics. Ruth, thank you for joining. What's on your mind?
Hey, I just saw this sketch of the different colors and so on, and I was wondering about the footprint of the lens system. Can you comment on that?
Yes, of course. The footprint of the lens system, it was just from a practical point of view, easier and faster to use our macroscopic setup. So a lens is a millimeter, 2 millimeter diameter. So you have between the laser diode and the PIC, you have 2 lenses of it may be a centimeter. The optical pass is a centimeter, but it's just for practical purposes. Yes, we could have done butt coupling or so, but it's for us, it was interesting to understand what the PIC can do or not. What are the facet losses? What is the absorption? What's the scattering for the different wavelengths? And we did not bother to do a lot of butt coupling. But this is the next step, yeah. But a centimeter, maybe optical pass. Cost of 0. A lens here is €10.
All right, and now we go to the medical market. Patrick, you're going to love this presentation. Ruth, you're going to also love it. We are going to go to a company called CareGlance. They specialize in OCT using photonic integrated circuits. Thank you very much, Maria Chiara, for joining the meeting today. The floor and the attention of everyone is yours.
Okay, let me share the screen. It's not in full mode, but perhaps. Okay, can you see it? Okay.
Yes.
So thank you for the introduction, Jose. I'm glad to be here in order to make you understand which are CareGlance PIC perspectives in real-time portable OCT generation. So what is CareGlance? CareGlance is a novel Italian startup which mission is to enable 1 MHz generation optical coherent tomography systems for effective real-time 3D imaging, thanks to an innovative ultra-fast swept source. Our solution is nowadays based on a microcomponent external cavity tunable laser structure, where the technological innovation lays mainly in 3 points. The first is the adoption of a novel Fabry-Perot component based on an ultrafast electro-optic material, an innovative control algorithm, and a well-consolidated assembly process thanks to a long-standing shareholders' experience in photonics technology. What CareGlance wants to offer is a very fast solution able to remove artifacts due to sample movements in OCT 3D imaging. And this is particularly important in healthcare, where intentional and unintentional patient movements can seriously affect the quality of measurements. The laser solution has a very small footprint, so enabling portable OCTs. This is, in our vision, the best way to support a doctor-to-the-home approach, both for diagnosis and follow-up of degenerative disease. And the solution is cost-effective because it's based on an easy and fast assembly process. So we are not talking about an idea for a good startup, but there are real prototypes. I don't know if you can see on camera. Okay, we have already developed prototypes for telecom applications, so with different materials and wavelength, but basically the assembly process is the same. So, which is our product strategy for the medium long term? We are not only interested in a discrete component ACTL structure, but we want to move through progressive steps along a couple of years in order to develop a fully integrated OCT micromodule, which can be transversally applied in several fields ranging from healthcare to industry. So, in our thought, we must start from a wafer level packaging where some fundamental components can be assembled in order to ease the scale up process. By now, for our first product, this is not so important as we target a healthcare sector where volumes are small enough to allow a unit by unit production process. But it will become a must if we want to target several industrial applications. So in my vision, we can think about an integrated, let's say, version of our swept source where a VCSEL is tuned by means of the ultrafast electro-optic material, and the output is addressed towards an OCT interferometric engine. By now I'm thinking about a silicon nitride platform as we work at 1064 nanometers, but we want to have a flexible design in order to meet different wavelengths requirement. So here the important novelty is to use the ultrafast material both for VCSEL tuning and both for beam deflection in the XY plane. The target is to integrate everything in a pigtailed module with an electronic control in a card-like shape. So I'm here essentially to understand something both from PIC manufacturers and from potential customers. So which are the sectors I want to address? First of all, healthcare, in order to allow real-time 3D tissue evaluation for diagnosis, but above all for surgery. The most important thing for a surgeon is to be able to pick quick and precise decisions during patient operation. But we want to move also to the automotive sector because OCT is becoming more and more important in line assistance to some industrial processes like remotely assisted laser welding, we are already seeing some important collaboration agreements between big automotive companies with OCT suppliers, like, for example, BMW with IntelliWeld, which happened like a couple of years ago. But in general, OCT can be extremely helpful in quality control for the production of any mechanical piece in order to evaluate in real time which can be subsurface defects like microfracturing and cracks. So in order to summarize, my interest from the PIC manufacturer part is to try to understand and review and optimize the design to target the fully integrated OCT solution, and to start programming the first trial runs, and to find novel areas and potentially interested customers to exploit the advantages of OCT in real time. So I'm here for any question. If you want to contact me, you see the email address. And thank you for your attention.
Thank you very much, Maria. Super interesting application. Yes. So okay. So well, we see what are you developing. So first of all, well, I would like to mention for you that you will be like the perfect user for MedFab. That, if you remember, is the pilot line for validating, testing, manufacturing of medical devices for sensing, and also to help you to go to ramp up production. And also, well, you mentioned it, silicon nitride, right?
Yes.
So maybe this is a good moment for, well, a potential collaboration for you, because we have here a great silicon nitride foundry. And maybe Anton, I don't know if I am wrong, did you prepare a slide for us?
Yeah, sure. Probably I can share it right now.
Yes, try to share. Maybe this is the right moment for you to explain what is LIGENTEC doing.
Okay.
Okay, perfect. Can you see the slide?
Yes.
Okay, then great. So thanks for giving me an opportunity to give a couple of words on this part right now. So I believe the majority of you knows LIGENTEC, and still probably I will briefly remind what we are doing for those who are not fully familiar. So we are a chip manufacturing provider, and our main expertise lays in the field of silicon photonics, silicon nitride-based photonic integrated circuits. And generally, we can address any volumes from low quantity early prototypes to real volume production. And here our unique know-how is SiC films, which gives very low loss features, much lower phase noise than for any other platform, which I believe is very important for many applications, including the sensing ones, and also allows for really small footprint of the devices, which could be a problem of some of the low index contrast platforms. And of course, our platform holds the same benefits of any silicon nitride platform, so wide transparency range from visible to mid-infrared, and ability to handle high powers, and of course, higher thermal stability.
Okay.
So going back to the topic of the sensing, so I believe as any good platform, we would like not only to promote the good fabrication capabilities and to provide the perfect material stack, but also to provide our clients and partners with really good and high-performing building blocks for any kind of circuitry or subsystem for their systems. Therefore, we propose as a part of our PDK and the process highly performing ring resonators with Q factors of 2 million and more, all the building blocks which you may need for any kind of circuitry, including all the OCT applications, such as very stable and performing splitters, low loss delay lines, and moreover, you can combine it in a functional block such as filters, switches, and multiplexers and demultiplexers, including AWGs. Probably it also goes back to the question from, or to the topic discussed by Patrick from TOPTICA, when you need to combine several wavelengths or you need to kind of multiplex or demultiplex several signals. Also, as we work with SiC films, it gives an access to all the nonlinear properties of the silicon nitride, and therefore to precision metrology or to gas sensing, for example. So here I mainly refer to possibility to generate optical frequency combs or supercontinuum. And generally in terms of sensing applications, one can foresee several main areas or domains probably. So it's sensing and microscopy, including biomedical and bio-related ones. It's signal routing and interrogation. It's time and frequency metrology, and also it's LiDAR and OCT applications. And therefore, coming back to the previous speaker, here probably we can have a good fit with your planning in terms of project and in terms of your product development, because we offer our capabilities in terms of silicon nitride fabrication and development of different subsystems based on silicon nitride photonics.
Okay, thank you very much, Anton. So I can see here a lot of potential collaborations for you. Now we have a question from Freedom Photonics, Milan. Hello, Milan, how are you? Where are you? I cannot see you. Long time no see you, Milan. And I cannot see you.
Hi, I'm here.
Hello, how are you?
Can you hear me? Well, no, the question was just what is the line width limitation on this sourcing for this OCT application?
We can reach, let's say, enough line width for OCT applications. It's something around several tens of centimeters. We have not measured it yet, but we can say this from our previous experience in short cavity external tunable laser. So the structure is quite the same. It's a matter of changing the emitting wavelength, which was previously 1550, and using a different fabric-row, but it could be in this range. 10 of centimeters coherence length.
And we have another question from Kevin from Eblana. Also, a long time no see you, Kevin. Where are you?
Hi,
do you want to proceed with
Eblana Photonics? Yes. Hello.
Hi, Maria Chiara, thank you for the talk. Just a quick question. So you're using an external cavity device, as you say, but is there any reason why you use that instead of, say, something like a more integrated chip, such as an SGDB or something like that, that could be maybe more easily integrated?
So let's say we have started this startup in order to exploit advantages that we already knew from past experience in liquid crystal. So the first approach is to build up the external cavity with micro components so as to get in the correct time to market window. We want to have a product within the end of 2022. As far as concerning the integrated version, and did you ask also for the sweep bandwidth? It was you?
Yes, that's me.
Okay, we can reach through our patented control algorithm a sweeping range around 100 nanometers. So this is enough for most OCT applications. The need to move further in order to think not just to the laser source, but to the fully integrated OCT module itself is to go forward, not to be simply a supplier for OCT system producers, but to target final clients, final customers, which can be, of course, clinics and surgeons, but also automotive industry. And I want this module to be easily integrated in every machine, thanks to few modifications at the design level and at operating wavelength level. So this is our scope.
Okay, thank you.
To create a flexible device that can have a strong impact in very different sectors.
Okay, so we still have two questions before to move to the next speaker. Dirk from Coherent.
Yeah, this is perhaps...
Hello, Dirk.
Yeah, hi. Perhaps, I don't know if this is a question for LIGENTEC or who is best to answer this, but I've heard a lot about silicon nitride as the material for the waveguides, but what about silicon carbide? How does that compare to using silicon nitride? Are there any advantages to silicon carbide compared to silicon nitride?
Any of the foundries in the room would like to answer this?
Yeah, so probably I can take this question, as I previously mentioned silicon nitride. So thanks a lot for the question, and I believe it's always quite a discussion depending on your application, target wavelengths, target system, and volumes, because it's not only a question of the material itself, it's always a question how it will be combined with all the other components, and the question how it can be fabricated in volumes, or whether it can be fabricated in volumes. So again, it's a bit hard to answer your question without knowing the particular details about what you target, but we're always happy to discuss if you have any idea in mind.
Of course, I'm sure you can discuss this application later. And well, there are other questions, and well, I will encourage you to keep in contact after the meeting, because I think now, after talking about silicon nitride, it's a very good moment to move to the next speaker, Santiago Simón from LUMENSIA. Silicon nitride biosensors, my favorite topic.
Hi, good afternoon.
Hello,
I will
Santiago.
share my screen.
Yes, please.
Okay, can you see it? Okay, I don't know if I can hear, you can hear me, I cannot hear you now. Okay, thank you. First of all, thank you to Jose and Anna and EPIC for inviting us to share our experience with you. Maybe we are the smallest company on stage today, and then maybe I will give you in 5 minutes an overview of what we are and what we are doing now. So we were founded back in 2013 by our mother company. This is Helia Photonics, a well-known company in the defense and space segments, because they perform quite nice projects for the European Defense Agency for biological threat detection. So it seemed at the moment that it would be a very nice opportunity to establish a brand new company to exploit that prototypes that were the outcome of that project for biological sensing in very high volume sectors like food safety, health, or environmental monitoring. That was the reason why it was created, and started the operation in 2015 and with the actual team. And this presentation is the result of 5 years of R&D projects and 2 investment rounds raised by the local big food industry. And then we are about launching our first products later this year. So what we implement is a particular ring resonator implementation on silicon nitride photonic integrated circuits. In order to perform a multiple simultaneous immunosite sensing scheme, that is what we do for real settings, is the determination of the presence and the quantification of multiple targets in a sample with the same sample. So what give us a very nice advantage in front of the way in which laboratories act by now, perform their tests by now. So one of the main things that we do is that we design all of our components and all the equipment, starting from the big design that we perform on our company, and we manufacture the first series, as you can see on your right-hand side of the screen, in the clean room of the Polytechnic University of Valencia, here in the same building, just 2 floors down, and then give us a very nice flexibility, rapidness, and the prototyping and independence in the development. So this is the timeline of our evolution in the last year, just to show the gray colored projects are from Das Photonics, in the beginning of all this of this company. And in color in blue are the projects for H2020 projects and also national project in which we have taken part, and that has led us to reach our degree of maturity by now. And we have now running 2 very important projects, and I will not go into detail of this project because of the shortness of the time, but we are now performing a spring project for the regional government for simultaneous detecting of antigen and antibody of COVID-19 for obvious reasons. We are performing already the validation with human samples of saliva and also blood serum, and we are performing quite nice. And then our mainstream is for food safety, and we are also implementing a fast track to innovation project awarded by the European Commission to foster the industrialization of our technology. So, being more concrete, this is our product. This is we call it safer, and we have two main components. We have we call an application agnostic biosensing platform. That is that it can be quickly adapted to many applications. That includes in a standalone system all the subsystems required to make the PIC integration: the optics, fluids, pneumatics, electronics, software, computing, communication, human-machine interface in a standalone portable system on only 4 kilos that is intended to be operated in laboratory environments for in a hospital or in a food industry laboratory and so on. And then the main component is the consumable cartridge where the PIC, the biofunctionalized PIC is integrated, and that you can see down here on the right. So as you can see, there are some reservoirs where the laboratory technicians pipette the sample, then she close the cartridge and then introduces the cartridge into the system, and then the system takes care of everything. And from the very beginning, they pressurize, they flow the samples over the sensors, and then make all the interrogation and all the quantification through the calibration curve for each one of the analytes. And in only 20 minutes, they get the results for the assessment of the concentration and presence of up to 6 different biological targets. So in front of we see in the food industry laboratories and hospital, we have different competitive advantages. First of all is that we are natively multi-analyte. With only one sample, we can determine the concentration of up to 6 different analytes. Which is very important to make a fast test. Then we are label-free. That is, we don't need any pre-treatment of the sample. So, which is very important because we are not making a fluorescence or a colorimetric evaluation of the sample. We are making a direct measurement, as you know, and so we are much more precise, and we take the most of the sensitivity of the proofs that are biofunctionalized. And we are also very, very cost effective. We are expecting a cost reduction for the testing cost for our customer about 80% of their actual cost, because they perform multiple chip testing in only one shot. So the first product that we are launching in the market is the multiple allergen determination for the food industry for meat, dairy, and bakery products that will be rolled out in the next months. We have been validating our technology in front of the certified laboratory results for all of our investors' range of products. That is for example, for rice, from pasta, for broth, or for meat. And we have very, very, very good results. And then we are launching that first product for allergen assessment in the next month. So it has been also awarded by a fast track innovation project by the European Commission. The first cartridge that will assess the content of gluten, milk proteins, and egg is almost ready and is going to be tested on factory on site later this autumn. And then 3 more cartridges will follow to complete a set of 4 different cartridges for covering 90% of the allergen testing needs of meat, bakery, and dairy dairy industry. So in this project, we have a very nice alliance with Nestlé, Eurofins Laboratories, National Food Institute for Denmark, and also with the University of Valencia. And so, last but not least, which are our plans for the near future. We are now, as I said before, we have an agnostic biosensing platform that can be implemented into different final application. And then, first of all, we are launching the allergen assessment in food matrices that will be deployed in the first unit later this year in some food manufacturers. And then we are also working very fast in the SARS-CoV-2, and the antibodies detection for COVID-19. And then we have some other running projects and products like for veterinary, for swine fever detection, and also for microbiology. That is one of the main headaches for the food safety issue, and also for the environment. Then we are working on a simultaneous E. coli, Listeria, and Salmonella testing, both for food safety and environment monitoring, that is for reduced water. So, and for what are our challenges for the near future, we will need the cooperation of the supply chain. Okay, we have to go to the industrialization of the system, and we have to be as robust as to be certified as a laboratory system. And then we have also to deal with the product cost upscaling. That is, we need to upscale, to grow, and to be able to produce lots and lots of cartridges, maybe for millions of cartridges as far as we are expecting. And then we have to deal with the cost reduction to be competitive in this market. So that's all for myself. Thank you.
Santi, this is impressive. I would like to say congratulations. I met you and Javier a few years ago, and you told me we want to go into the biosensing path. You've been so fast. It's impressive.
Thank you very much.
Congratulations. This is incredible. This is what Europe needs. Thank you for doing this leap on bringing industrialization of photonic integrated circuits in this amazing market. All right. So let's.
Last step is still missing. So we have to go to the last step to go to the market. It's the real proof.
But everybody's here to help you on that. And the first one who wants to help you on that is ST Microelectronics. They just contacted me. They say that you are talking about the cartridges, but the actual unit is a bit bulky in their opinion. They say that is there a way, a roadmap towards miniaturization of that?
Okay, it depends on the application, because it could be miniaturized, but in front of the actual system that our potential customers are using, it's much cheaper and it's smaller. So we are, for the market we are assessing by now, we are pointing at, it's quite nice. So of course everything can be miniaturized, and we have to do less volume and less weight, but it's not a limitation in the market by now. The limitation by now, it's the high volume manufacturing that you have to deal with. Because only for the allergen market testing, that is at Europe today, about 10 million tests are performed by year. So if you reach to this market, you should have the possibility of upscale your manufacturing volume for cartridges and for PICs. So we are also in contact for some of the people in the audience, of course.
In the beginning of the meeting, Santi, there was a question from Peter Harsma from TNO. He put in the chat, and I said to him, we are going to come back after the presentation on LUMENSIA. Peter, what was on your mind then?
Yeah, that was actually not related to biosensing. Thank you, Jose. So I'm here with a double hat, actually. So I work for TNO, which is a Dutch research organization, but I also am involved in a biosensing startup. And we work on instrumentation for ring resonator kind of sensor chips. So in that sense, I'm not sure we are competitors, maybe we are. But the scope of my question was actually different. So we have applications like spectrometry, LiDAR, measuring displacement, OCT, and then many people who package photonic integrated chips, they work with fibers. And sometimes you don't need a fiber because you really want to interact directly with your object. So I was wondering about the packaging opportunities for free space coupling to an object to be sensed. And I was wondering if maybe Fix or Technobis or Peter O'Brien could comment on that. I don't hear you, Jose.
All right, so let's ask them. They're here. So let's go to Jeroen Douwe from Fix. PICs is one of the key companies that we have in EPIC. It's like the European OSAT for manufacturing package PICs. Jerome, we have a question from Peter asking about free space coupling into a photonic chip without the use of a fiber. Is there anything, is PICs working on that somehow? I have you muted.
Okay, thank you for the question. Sorry for not getting to find your mute button. So I think free space coupling, we have various configurations. So it's either by using lenses and then going through the sidewall of a package. So it can be like a glass cap where you're going through. And on the other side, we're using a lot of interposers from companies like Team Photonics that you don't need to have the free space configuration. So still have a fiber attached, but you can adapt the modes of the fiber with the adapts to the modes of the chip. So I think it all comes down to what is the application actually. You also have the caps of the TO cans that you can put on top, and you have the orthogonal coupling of the light coming out of the chip.
I think Peter is nodding along. I know you guys know each other very, very well, so I'm sure there is ways to collaborate. I will post the question for later answer from Peter O'Brien, but I want to go back to Santi because I really love your presentation, but we really want to help you. Can you share with us a couple of challenges, a couple of room for cooperation that we can make the right introduction today?
Yes, one of us is we need the tunable lasers in the mid-infrared or near infrared, very, very cheap and fast and accurate.
What wavelength in the near infrared?
From 1 to 2 microns, in that range.
Okay, so we will make the right connection. I don't know what cheap means, but cost effective is something I like to say a lot. Fantastic. Thank you very much, Santi. And once again, congratulations. This is exactly the kind of things that we need to have more often develop. I'm really happy that from DAS Photonics, from a group of very, very smart people, they managed to make this very important step in the manufacturing of PICs for a clear application. And let's go to a company that for many years already have made this jump from wafer to product vertically integrated and foundry, Lionics in Enschede, the Netherlands. My very good friend Douwe. Douwe, goedemiddag. How are you doing?
Hi, goedemiddag. Yes, let me share my screen. So here it is. Yeah.
Just for a second, you saw there the light structuring that they managed to do also out of a chip. But let's talk about sensors.
Let's talk about sensing applications. Yes. So a bit about Lionics International. So we provide customized solutions for OEMs and system integrators. So we don't have our own products. We always design it for our customers. And we do that by vertical integration, which means that we can do the design, manufacturing, and also assembly as well. So it's we always, so that's one of our slogans there, that a PIC is more than a chip, right? You always need to know what you do with the lights or whatever signal goes into your chip, and do that in a way that you can scale the product volume. So one of the things that we work on strongly to use it as a prototype, because many of our customers are investigating new things, but they all want to scale at some point. So and we support that in several routes. We do a lot in photonic integrated circuits. On the right, you see we do much more than that. We have a strong background in MEMS, especially what we call customized MEMS. So the MEMS things that the large MEMS foundries will not take up. And we do a lot of optofluidics or fluidics, and also combine that with integrated photonics. And that brings us later today to one of the sensors that we are working on. So for photonic integrated circuits, we have a silicon nitride based technology called triplex, which is very low loss, which can taper very well to different mode sizes, which can operate from 400 nanometer to 2350 nanometer. And we do a lot of hybrid assembly with semiconductor materials. So I have a few examples, and it has been told already a couple of times that you need to integrate somewhere a laser. We can attach a semiconductor laser, indium phosphide or any other material. We can either butt couple it towards our chip, or we can use a wafer scale process to do that. So that's here. So about sensing applications, we have many customers in sensing applications. Working on silicon nitride means that the application scope is very broad where you work in, and has been generally out of the telecom range. So we have a strong background in sensing. I brought two examples for the wide spectrum of sensing applications for PICs. One is the DNA sequencer that we have worked on for Pacific Bioscience. This was basically a 1x-n splitter that they used in their DNA sequencing system to have very well control over location of some of the light where they did the sensing there. This was green light, 532 nanometer light, 300 milliwatt lasers were attached to that. So in feedback on what Patrick Leisching was mentioning, yes, we can get. We always say if you can bring it into a single mode fiber, you can bring it into our silicon nitride waveguides. And the issue you have there is getting the light in and out, right? You need to take care of not breaking your interfaces. So this assembly also was fitted with an end cap to ensure that the assembly will survive over the lifetime of your module there. The 1x-n splitter had a very good accuracy there both over the splitting ratios, but also over the different components there. And in the end, it was a plug and play install, right? The DNA sequencer part is a very complex system to build, and this module just needed to be plugged in, fiber plugged in, screw holes to adapt, because it's just one of the 100,000 parts which goes in there, right? And that's so we all think that photonic integrated circuits is the key component of many systems. Now, in this case, it's just a component to make it work, but without it, it will not work. On the other part, something that we have worked on a long time, it's the photonic biosensor, silicon nitride based, both microring resonators, but also asymmetric Mach-Zehners, where you can have a silicon nitride chip with multiple channels with selective surface modification, which means that we only, together with our partners Surfix and Curin, we can do a selective surface modification. So only do a surface modification, only make it active on top of the silicon nitride to have very high sensitivity of the sensor. And it can be used for virus detection. Now, of course, we have a strong COVID push on that, and we are working on getting it to operate for that application as well. The main development in the past was for different kind of DNA and cancer markers. The platform here also, we think about not only the chip, but about the whole system. So it can be integrated with a VCSEL and a detector as well, so that it becomes a standalone sensor that can be produced in mass applications there. So what is Leisching looking for? So we have a very nice technology, silicon nitride. We have many capabilities of assembly and making modules and making actual usable systems out of it. But we don't have the application knowledge, right? So we always look for application partners who bring us their who bring their issues, and we try to solve that, right? And one of the things that we have been working on the bottom part is the narrow line with tunable laser. So we can, with a hybrid assembly, we can integrate a gain section to an external cavity mirror in silicon nitride to make a very narrow line with tunable laser. We can do the same. So this is a preview just for this consortium here, a preview of an assembly of a green laser diode towards a silicon nitride diode. So it's a direct butt coupling of a green laser diode to a silicon nitride chip for different kind of applications, structured light, AR, VR, but also in the life science and medical world that can be done. We can make spectrometers, we can make OCT systems, all these things, and yeah, basically want to contact people with ideas. So hopefully you'll have many ideas.
Okay, thank you very much, Douwe. Super interesting presentation as usual. Give us, well, you know, give us one challenge. I mean, give us one challenge. I don't know, in the packaging, maybe in the fabrication of PICs, in automation. What would you like to find? Douwe?
Sorry?
Hello.
Yeah.
Do you want me
last part of your question didn't came over. Sorry.
Sorry. So just one challenge. I mean, in order to further develop your products, where do you think that is the bottleneck? Is in the packaging, or do you have any requirement for the fabrication of photonic integrated circuits, any kind of new machine?
So I think the challenge is always in making a module out of it, right? And it's part of the product development routes that you use with your end user application partners there. And I think in photonic integrated circuits, both in silicon as well as silicon nitride, we really came from the research area, and we are now into the world where we are into product development routes. And I think the main issue there is packaging and scaling.
Okay, and we have plenty of companies here that can help you with that. Well, I would like to, maybe this is a good moment for me to introduce you a new EPIC member. So we are very happy to welcome at the EPIC family and a spin-off from AMO, Black Semiconductors, and we have here Daniel. Hello, Daniel. Okay, would you like to explain us, I mean, in 1 minute, what is a Black Semiconductor doing?
Yes, thanks. I share my screen that you can see a sketch. Thanks, Anna, very much for the chance to say hello here to the community. We are a very young company, started in the beginning of this year. And what are we doing? Two things. First thing is the outlook, where do we want to go? And then what is our first product? So the outlook is where we want to be in a couple of years is fabricate photonics directly on any electronics. So there's an electronic circuit, whatever it's doing. It might be the electronics to process data in a sensor, and then the photonic circuit is directly fabricated on top of this electronics. No bonding and everything monolithically on the wafer, directly fabricated in silicon technology. How does that work? So we use graphene. These active devices that are sketched here are graphene devices. They are very broadband. What we're doing today is the standard telecom range from, let's say, around 1300 to 1600 nanometers. And also we tested down to around 2 micron. They are very, very fast, these devices. Up to 130 gigahertz is what we measured on chip. And we have packaged devices which will work up to 50, 67, or even above 100 gigahertz. DC responsivity is in the range of 2 amps per watt. So that's the outlook. We want to end at an integrated optoelectronic chip. And we are looking here for partners who have a problem with an electronic circuit that they want to solve optically, directly integrated. That's the one thing. And the other thing is a photodetector, which is our first product we are going to release soon. It is for telecom applications, but it is also a version available at around 2 micron, which is interesting for sensing. The main feature is it's super fast. That's in a nutshell what we are doing.
Thank you very much, Daniel. Okay, so you are open for collaborations with companies that want to put your graphene on their electronics. Perfect. So thank you for that. And well, now if there are no more...
I have a question in YouTube from the YouTube universe. Still there. Soitec is asking. Soitec is one of our key members in developing silicon insulator wafers. And the question is about the VCSELs that were presented by Douwe. They're wondering why use silicon nitride VCSEL integration? Why not an etch emitting?
It's a good question. It depends on the application. The fixtures that we have used for the biosensing platform are very, very cheap. It's basically the fixtures from your mouse, right? So that's available volume that you use there. For other applications where we use butt coupling for example for the narrow line with tunable lasers, we do a butt coupling because it gives the best coupling from silicon nitride to the semiconductor, and the lowest losses, since it's a intercavity interface, it needs to be low loss to get these narrow line widths. So
and reading the mind of Herman Moss from ficonTEC, because we think alike, and also reading the mind of Gregory from ficonTEC, can you actually place the VCSELs with passive alignment?
We can do that, yeah. We have, based on our vision system, actually, we have a patent on that, so you can overlay it, and you can see it, or the machine can do it automatically. So basically, yes, this is what we are doing.
I think there is an obvious path for cooperation here. Back to Anna.
Yes, sorry. Okay, no, if there are not other comments or other questions, let's move ahead with the last but not least talk of this meeting. So, Frank Smith from Pilot Photonics, you want to share your screen? The floor is yours.
Thank you. Let's share this. Okay, can everybody see and hear me?
Yes, very well.
Great, thank you. Yeah, so I'm just going to give a talk about a quite early stage sensing technology that we've been working on within Pilot Photonics around the area of monolithic dual comb photonic integrated circuits for optical sensing, and we're applying these both to gas sensing and to FPG fiber Bragg grating based temperature and strain sensing. So very briefly, Pilot Photonics is an Irish company creating PICs based on our comb source technology, and we're applying them in many different areas: data transmission, sensing, high frequency metrology for the European Space Agency, and many other areas. And so just very briefly on our technology. So optical combs, as most people know, are lasers that produce multiple coherent frequencies of light simultaneously. They're a powerful tool for many photonics applications, but particularly for fiber sensing and spectroscopy. We use gain switching, as I mentioned, and it's a flexible, cost-effective approach, very well suited to photonic integration, because it's just based on the direct modulation of a semiconductor laser. So another kind of nice aspect that this brings, so essentially what you do to generate your comb is you drive your semiconductor laser with an RF sine wave, essentially. And you see that you can get this nice swept mode that the animation is showing there, which is not typical of most comb sources. Most comb sources are based on a fixed physical cavity, and it's tough to get such kind of broad modulation of the wavelength spacing. So that's a nice aspect that can be used for spectroscopy and sensing. I kind of stole this kind of message which I like, which kind of explains the benefits to using comb for these applications quite well, from a magazine article quite a while ago. But I think most people are familiar with the phrase you can't see the wood for the trees. Well, the typical spectroscopic approaches used today are either use a broadband light source, and this lets you see the big picture of what you're trying to measure, but it doesn't let you see the detail quite so well. Alternatively, as a number of today's speakers spoke about, You can use a narrow line width single mode laser, which you sweep across the spectrum, and this lets you see the detail. This lets you see the trees, but at any particular time you can't see the big picture then. Well, an optical comb source allows you to see the woods and the trees at the same time. So it offers, and PIC-based comb sources offer the potential for high resolution, high speed, very small footprint, low cost, and high sensitivity. And we can take it one step further by using dual comb spectroscopy. So essentially here what you do is you create two combs very slightly offset from each other in wavelength and wavelength spacing. And essentially you pass one of them through the sample and one of them is used as a reference. And then they mix together on a photodetector. And what it does is it transposes the measurement down into the kind of very low frequency RF domain. And what that does is it eliminates the need for an optical spectrometer, essentially by transposing this measurement. And then you can detect and analyze and measure the signal using essentially very, very low cost silicon system on chip sort of things at a couple of dollars of price point. The next two slides are essentially kind of basically descriptions of a couple of research papers that have been published recently by our partners in this area. The first is on a kind of a full gas sensing setup using this dual comb architecture. And then the next one shows the PICs that have been fabricated by Tyndall to essentially implement this dual comb architecture in PIC format. So on this slide, I'm not going to go into it in too much detail, the reference is there, but essentially what you do is you create two combs and you lock them together using a single master laser, so they become synchronous, and they're very slightly offset in wavelength and in free spectral range. And you pass one through the gas sensing setup. In this case, it was H2S, hydrogen sulfide in air. And the other one is used as a reference. And essentially then you just couple the two of them together and beat them on like a 15 megahertz photodetector, so very low speed photodetector. And what results is essentially a comb, but in the electrical domain, in the RF domain. And what you can see if you zoom into that comb on the right, very right most spectrum there, is you can start to see the absorption of the gas species as you increase the pressure of the pressure and concentration of the hydrogen sulfide in the cavity, and that is matched quite well then to the HyTran database. So you can look into that in more detail at that reference. Next step then obviously is to turn that into a photonic integrated circuit. So we've been working with Tyndall who have been fabricating gain switched comb sources, and this is a fairly funky one which has both two comb sources as well as a tunable master laser in a 1 millimeter PIC footprint, 1 millimeter squared PIC footprint. So essentially what you're doing there is you have two comb sources that you gain switch using an RF signal, and you injection lock each of them using a single master, and so it synchronizes the two combs, and then by having your free spectral range of the comb slightly offset, you can again create that beat pattern between the two combs on your photodetector. So these PICs have been fabricated, tested. Again, the initial characterization has been published in the link below there. And these are being packaged, I think, at the moment by Bay Photonics, and will be put into the system then that was presented on the previous slide. So essentially, what it does is it gives you kind of real-time, very high speed, high resolution measurement of gas or of fiber Bragg grating based kind of sensors in a very low cost approach. So that's the idea. Other related applications that we're using are comb sources for in sensing and spectroscopy. As I just mentioned, the fiberbrad grating-based approach for temperature sensing. We're also working with the European Space Agency and the University of Neuchâtel on rubidium spectroscopy for atomic clock generation. So in the image here, you can see a kind of initial benchtop prototype that was built, and we've now fabricated photonic integrated circuits using this comb source technology for CPT atomic clock generation. Finally, then, just to go to the kind of template that the EPIC guys have requested, and I want to say thanks to EPIC for asking us to present here, and also to our collaborators on these on this work. But essentially, what do you do? Well, we apply our innovative PIC comb source technology to deliver bespoke photonic solutions for applications in data transmission, sensing, and metrology. What do we offer in the sensing world? It's a very low-cost approach to optical sensing using PIC-based, monolithic PIC-based dual comb spectroscopy. And really, our business model is quite flexible. We can either, for low volume applications, we can supply these as products, modules, or essentially just the PICs themselves, or for high volume markets, which is what we think can be enabled by this. We're very open to licensing the technology into customers who are more facing who are at the application level and are building and shipping photonic sensing systems. And really, that's what we need. Is we don't ever intend to really roll this out as a pilot photonics product. Our business model is more about designing the solutions and then partnering with our customers to use the innovative technology and bring the technology to market. And that's whether it's in the sensing side of things or in the telecoms, datacom side of things as well. And then finally, I think, as everyone today has recognized and touched on, I think packaging is critical to this, keeping that packaging cost down. Otherwise, you lose a lot of the benefits of going to photonic integrated circuits. So I think one aspect to this is the use of a comb as opposed to individual lasers. You do get that, you can get that benefit because you can replace multiple lasers or multiple PICs with a single comb source. So you do potentially get and you only have to package one, so you potentially get a good saving there in terms of cost on the packaging. However, I think it's really more greater innovation is needed, as a few people have talked about today, in order to really drive the cost out and make this a product that's commercially viable in the very high volumes.
Thank you very much, Frank. Actually, it is clear that you have made a huge involvement on the reduction of the cost for the multi-wavelength laser, and we want to connect you more and more with the spectroscopy companies. It's clear where you are in the value chain and what kind of challenges, but mostly we want to partner you with companies who need cost-effective light source for spectroscopy. We are gonna ask you a question from the YouTube universe. Is Jan Vermeeren from Caleste. They are wondering, can you use the reference signal also as a local oscillator to amplify the signal?
That's very interesting. Yes, you can is the answer. So on chip, we can also, as well as generating the comb on chip, we also have an approach to demultiplex any one of the lines and any one or more of the lines. And we use this in the telecoms space because each line of your comb needs to be modulated with data. So yes, you can take that master and use it as a reference, and you can also individually demultiplex any one of the lines and essentially interact your master laser with the demodulated or demultiplex comb lines on chip. So that's very powerful, and I think I know what that person is asking about, and it's a very innovative and unique approach.
Thank you very much, Frank. I think you need to discuss this offline with Masoud from Nanoplus, with Patrick from TOPTICA. We have people from Teraxion. There is clear cooperations here. I hope that we managed to find the real laser, cost-effective laser for spectroscopy, and you're on the money there. Congratulations, Frank. It's been a great meeting. It's 17 minutes later. I feel really bad about this, but I know many of you are staying in the channel because we're doing the one-to-one meetings afterwards. But I would like to say it was a fantastic meeting. It was great to have, and I worked really hard on getting the right companies in the room, and we managed to, first of all, it was clear it is still all about packaging and test. We really realized that, but we also saw huge steps into bringing photonic sensing into the market. Integrated photonics are now in key applications. I love the active video from Technobis. The LiDAR solution from Omnitron sensors are extremely promising. We all need to help Eric on this. Electrolux was talking about a roadmap for gas sensing based on mid-infrared, and that was really super interesting. TOPTICA was talking about different multi-wavelength laser solutions. CareGlance wants to put an OCT in the market. LUMENSIA is really telling us about biosensors. That for me, Santiago was the star of the show today. What an amazing achievement by LUMENSIA. DNA sequencing and also biosensing was presented by Ionics, and we finished with optical comms from Pilot Photonics. The challenge is still is cost effectiveness on the packaging and test. We didn't speak too much about test, but I know still is also a challenge. And the light sources for many of the applications, especially the mid-infrared, we have quantum cascade lasers. Nanoplus, Thor Labs can help us on that, but it's still a huge challenge. We need a gallium nitride foundry in Europe, so I would like to highlight that. We need a gallium nitride foundry in Europe because we have many applications on the visible wavelength range. And finally, we are seeing from the EPIC meetings a huge interest on automotive applications. Today we had Continental in the room. Last week we had companies like Fiat, like Audi, and they are asking about challenges and help and room for cooperation. That's why we need to learn from SUS Micro-Optics and get more automotive qualified companies. I know, for example, that FIX is already developing big products for automotive. We need to push this because it's a huge opportunity. I would like to thank everyone for a great meeting today. I think we are really making a difference with these meetings. We continue, so please stay tuned and join the rest of the EPIC meetings. Anything that you need, we are more than happy to have an incredible team of people who are here to connect with you. So don't forget, the most important part of the meeting is the follow-up. If you want to be successful, just make sure that you interact with the other people. I'm going to introduce many of the companies here, but if you would like to be introduced to any company, send me an email, jose.pozo@epic-ask.com. It's been a fantastic experience, and it's going to continue. The online technology meetings are here to stay. Even when you start traveling soon, and I know we are all going to travel as soon as we have a vaccine, we'll continue doing things online because we did realize that being online is very effective. It was 2 hours and 20 minutes of your time, and I'm sure many of you have at least one lead to follow up. Until the next time, be epic. Bye-bye.